August 12, 1943, Krupp Shipyard, Kiel, Germany. Engineer Karl Heinrich stood waist-deep in the icy Baltic Sea, his gloved hands adjusting a rubber seal on the hull of the Panzerkampfwagen 8 Maus. But this was no ordinary tank. The 188-ton behemoth had been modified with cylindrical steel snorkel, waterproof hatches, and a ballast system that let it submerge to 15 feet. Heinrich pressed his ear to the hull, listening for leaks. Behind him, a team of Krupp workers struggled to secure a 10-foot propeller to the tank's rear. One of two added to push it through water. The air smelled of diesel and salt. Above, Luftwaffe fighters circled, guarding the secret test from Allied reconnaissance planes. Heinrich stepped back, wiping water from his face. "Start the engine," he called the crew inside. If this worked, Germany would have a weapon that could cross rivers and seas undetected, invading Allied-held coasts before anyone saw it coming. The underwater tank was born from Germany's frustration on the Eastern Front. By 1943, the Red Army had destroyed thousands of German tanks, many trapped on the wrong side of rivers when bridges were blown up. Hitler demanded a solution, a tank that could swim across water barriers, bypassing enemy defenses. The Wehrmacht's Ordnance Office turned to Krupp, Germany's leading arms manufacturer, which had already built the massive Maus-heavy tank. Krupp's engineers, led by Heinrich, were tasked with modifying the Maus to operate underwater. The goal was audacious: create a tank that could submerge for up to 30 minutes, travel 2 miles underwater at 4 miles per hour, then surface and fight immediately. It was a weapon that would redefine armored warfare, if it worked. But the underwater tank was also a gamble. The Maus was already a controversial project, slow, expensive, and prone to mechanical failure. Adding underwater capabilities would only increase its complexity. For Heinrich and his team, the challenge was not just engineering. It was convincing Hitler and the Wehrmacht that the risk was worth it. The technical foundations of the underwater tank trace back to 1939, when Krupp began experimenting with waterproofing light tanks like the Panzer II. Early tests used simple snorkels, steel tubes that let the engine breathe while the tank waded through shallow water, but these only worked in 3 feet of water. By 1941, the team had developed a submersible kit for the Panzer III, rubber gaskets for hatches, a sealed engine compartment, and a snorkel that extended 6 feet above the tank's turret. This kit let the Panzer III submerge to 10 feet, but it was limited. The tank could only travel 500 yards underwater before its batteries, power in the propellers, died. The Wehrmacht used these modified panzers in the 1941 invasion of Yugoslavia, crossing the Sava River undetected. But the kit was fragile. One tear in the gasket, and the tank would flood. Hitler wanted more, a tank that could cross the English Channel, not just rivers. The Maus, with its thick armor and powerful engine, seemed like the perfect base. Modifying the Maus for underwater use required solving 3 impossible problems. First, buoyancy. The Maus weighed 188 tons, most of it steel. To float, it needed additional buoyancy, something that wouldn't compromise its armor. Heinrich's team added 2 20-foot-long steel pontoons to the tank sides, each filled with compressed air. When the tank needed to submerge, the pontoons were flooded with water. When it needed to surface, compressed air pushed the water out. The pontoons added 30 tons to the tank's weight, but they let it float with 6 feet of hull above water. Second, propulsion. On land, the Maus used a 1,200 horsepower diesel engine to reach 12 miles per hour. Underwater, that engine would stall without air. So the team added 2 electric motors, each powering a propeller connected to a bank of lead-acid batteries. The batteries could power the motors for 30 minutes at 4 miles per hour, enough to cross a 2-mile stretch of water. Third, life support. The 5-man crew needed air to breathe while submerged. The solution was a closed-circuit oxygen system. Chemical canisters that absorbed carbon dioxide and released oxygen, similar to those used in U-boats. The system could keep the crew alive for 45 minutes, 15 minutes more than the battery life, a safety margin Heinrich insisted on. The first prototype, codenamed Sea Devil, was completed in June 1943. It retained the Mouse's original 128mm main gun and 75mm secondary gun, both waterproof with rubber caps. The turret was fixed in place underwater to reduce drag, but could rotate once the tank surfaced. The hull was lined with 2 inches of rubber to seal leaks, and all hatches were fitted with double gaskets, layers of neoprene that compressed when closed, blocking water. The snorkel, made of 8-inch steel, could be raised or lowered from inside the tank. When lowered, it sealed the hull completely. Heinrich's team spent 6 weeks testing the Cetaphil in Krupp's indoor tank pool, simulating different water depths and currents. The first submerged test lasted 10 minutes. The tank descended to 10 feet, traveled 100 yards, and surfaced without leaks. The crew reported no issues with oxygen. "It's stable," Heinrich wrote in his test log, "but we need to test it in open water." The open water test, scheduled for August 12, 1943, was fraught with risk. The Cetaphil was transported by rail to Kiel, then driven to the Krupp shipyard's private dock. At dawn, the tank rolled into the Baltic Sea, its pontoons inflated. The crew, 5 Krupp engineers, including Heinrich, climbed inside, sealing the hatches. The snorkel was raised, and the engine roared to life, though it would be shut down once submerged. A small flotilla of patrol boats surrounded the tank, ready to rescue the crew if something went wrong. At 9:15 a.m., Heinrich gave the order to submerge. The pontoons were flooded, and the Cetaphil sank slowly, the snorkel's top the only part visible above water. Inside, the crew turned on the electric motors. The tank lurched forward, propellers churning. Through the periscope, Heinrich watched the seabed pass by, sand, seaweed, the occasional fish. The oxygen system hummed, and the temperature held steady at 65 degrees Fahrenheit. For 25 minutes, the Cetaphil traveled underwater, covering 1.8 miles. When it surfaced, the crew opened the hatches, gasping for fresh air. The hull was dry. The motors still worked. The test was a success. Word of a Cetaphil reached Hitler within days. He demanded a demonstration at his headquarters in East Prussia. On September 5, 1943, the Cetaphil was transported to a lake near Rassenberg, where Hitler and his top generals, including Field Marshal Erich von Manstein, watched from a viewing stand. The tank submerged, traveled 500 yards and surfaced, then fired its main gun at a target on the shore. The shell hit dead center. Hitler clapped enthusiastically. "This will win the war," he told Heinrich. "Build 100 of them. We'll use them to invade England." But von Manstein was skeptical. He pulled Heinrich aside after the demonstration. "It's impressive," he said, "but can it fight? The Mouse is already slow on land. Adding pontoons will make it slower. And what if the snorkel is hit by enemy fire?" Heinrich had no answers. The Cetaphil was an engineering marvel, but it was still a tank, and tanks needed to fight, not just swim. The Wehrmacht approved production of 100 underwater Mouse tanks in October 1943. with the first delivery scheduled for June 1944. Krupp expanded its Kiel shipyard, building a new assembly line dedicated to the Cetafel. Workers were pulled from other projects, including the V-2 rocket, to speed up production, but problems emerged immediately. The pontoons were difficult to manufacture. Each required 5 tons of steel, and Krupp's mills were already strained by demand for battleship hulls. The electric motors, sourced from Siemens, were prone to overheating underwater. In one test, a motor burned out after 15 minutes, leaving the tank adrift. The oxygen canisters made by BASF were in short supply. BASF was prioritizing chemicals for the V-1 flying bomb. By December 1943, only 5 Cetafels had been built. Heinrich begged the Wehrmacht for more resources, but his pleas were ignored. The Eastern Front needed more Panzer IVs and Tigers, not experimental underwater tanks. The underwater tank's first combat test came in January 1944, during the Battle of the Dnieper River. The Red Army had pushed German forces back to the west bank of the river, blowing up all bridges. The Wehrmacht needed to cross the Dnieper to reinforce trapped troops on the east bank. 3 Cetafels were deployed, along with 20 regular panzers. The plan was simple. The Cetafels would submerge, cross the 1-mile-wide river, surface on the east bank, and secure a beachhead for the regular tanks, which would cross using temporary bridges. At 3 a.m. on January 18th, the Cetafels rolled into the Dnieper. The water was 34 degrees Fahrenheit, and ice floes floated past. Inside the lead tank, Heinrich monitored the depth gauge, 12 feet, stable. The electric motors hummed. Then disaster struck. A Red Army patrol boat spotted the snorkels and opened fire with a machine gun. 1 bullet punctured a pontoon. Water rushed in. The tank began to sink. Heinrich ordered the crew to surface, but the flooded pontoon pulled the tank to the left. It capsized, trapping the crew inside. The other 2 Cetafels aborted the mission, surfacing and retreating to the west bank. The regular panzers never crossed. The trapped crew drowned. Heinrich stood on the riverbank, watching the Cetafels snorkel disappear under the ice. "It's not ready," he said quietly. The Dnieper disaster led to a reevaluation of the underwater tank. The Wehrmacht's Ordnance Office conducted an audit, finding that the Cetafel had 3 fatal flaws. First, the pontoons were too fragile. A single bullet could puncture them, sinking the tank. Krupp's engineers tried reinforcing them with 1/2-inch steel plates, but this added 5 tons to the tank's weight, reducing its underwater speed to 2 miles per hour. Second, the electric motors were unreliable. Siemens modified the motors with waterproof insulation, but they still overheated in cold water. Third, the tank was too slow on land. With pontoons attached, the Cetafel could only reach 8 miles per hour, half the speed of a regular Panzer IV. This made it an easy target for enemy anti-tank guns once it surfaced. The audit recommended halting production until the flaws were fixed. Hitler, furious at the Dnieper failure, agreed, but he refused to cancel the project entirely. "Fix it," he told Heinrich. "We need this tank." Heinrich's team spent the next 3 months redesigning the Cetafel. They replaced the pontoons with internal ballast tanks, built into the Mouse's hull. This eliminated the risk of puncture, though it reduced the tank's ammunition capacity by 30%. They swapped the Siemens motors for more powerful ones made by BMW, which could handle cold water. They also added a second snorkel, a backup in case the first was damaged. The modified Cetafel, codenamed Cetafel II, was tested in March 1944 in the Baltic Sea. It submerged to 18 feet, traveled 2.5 miles, and surfaced without issues. The crew reported no motor overheating, and internal ballast worked perfectly. The Wehrmacht approved production of 50 Cetaphil Tus, with delivery starting in August 1944. But by then, Germany's situation was collapsing. The Allied invasion of Normandy on June 6, 1944, changed everything. Krupp's shipyards were bombed repeatedly by RAF and USAF bombers, destroying the Cetaphil II assembly line. Steel and rubber supplies were cut off by Allied submarines, which sank 80% of Germany's cargo ships. The Wehrmacht diverted all available tanks to the Western Front, leaving none for the underwater project. By September 1944, only 12 Cetaphil Tus had been built. Most were stored in a bunker near Kiel, never seeing combat. Heinrich, now a captain in the Wehrmacht, was sent to the Eastern Front to command a regular tank unit. He left the underwater tank project behind, though he kept a notebook with test data and designs, his only record of the years he'd spent on it. The final chapter of the underwater tank came in April 1945, as Allied forces closed in on Kiel. The Wehrmacht ordered the 12 Cetaphil Tus destroyed to prevent them from falling into Allied hands. Krupp workers flooded the bunker, submerging the tanks in 20 feet of water. They then planted explosives, collapsing the bunker's roof. When British troops reached Kiel in May 1945, they found only rubble and a flooded pit. No one knew about the underwater tanks until Heinrich, captured by the British, revealed their existence during interrogation. A team of engineers was sent to bunker, but the tanks were too deeply buried to recover. They remain there today, rusting under the Kiel shipyard. Silent proof of Germany's failed dream. For Heinrich, the underwater tank was a lifelong regret. After the war, he was interned by the British for 2 years, then returned to Germany to work as a civilian engineer. He never spoke publicly about the Cetaphil, though he kept his notebook until his death in 1979. In 1998, his daughter found a notebook in his attic and donated it to the Deutsches Museum in Munich. The notebook, filled with sketches, test logs, and Heinrich's handwritten notes, revealed the underwater tank's true potential. It also showed the cost, pages of entries about failed tests, dead crew members, and the constant pressure from Hitler to hurry up. "We were building something that didn't belong in this war," Heinrich wrote in a 1944 entry. "It's too advanced, too fragile, too late." The underwater tank's legacy is a study in missed opportunities and overreach. It was a weapon ahead of its time, the first armored vehicle designed to operate both on land and underwater. Its innovations, internal ballast systems, closed-circuit oxygen, waterproof weapons, would influence post-war amphibious vehicles like the U.S. M113 armored personnel carrier and the Soviet BMP-1 infantry fighting vehicle. But in 1943 to 44, it was a luxury Germany could not afford. The resources poured into Cetaphil, steel, rubber engineers, could build 500 regular panzers, which would have been far more useful on the eastern and western fronts. The underwater tank was a product of Hitler's obsession with wonder weapons, a belief that a single revolutionary weapon could win the war. But war is not won by gadgets. It is won by reliable, mass-produced weapons and the men who use them. Today, the underwater tank is remembered as one of WWII's most fascinating what-ifs. Military historians debate whether it could have changed a war if deployed earlier and in larger numbers. Some argue that 100 Cetaphils could have disrupted the Normandy invasion, crossing the English Channel and attacking Allied beaches from behind. Others counter that the tank's flaws, slowness, fragility, limited range, would have made it easy prey for Allied destroyers and fighter bombers. The truth is unknowable. The underwater tank never got the chance to prove itself in large-scale combat. It remains a prototype, a relic of a regime that bet everything on technology instead of strategy. The underwater tank also offers a window into Germany's industrial and scientific capabilities during World War II. Krupp's engineers managed to build a 188-ton tank that could submerge, an extraordinary feat given the materials and time constraints. They solved problems that would not be fully addressed by amphibious vehicles until the 1950s. But their work was undermined by the Nazi regime's priorities, Hitler's demand for quick results, the diversion of resources to other projects, and the refusal to acknowledge the tank's fundamental flaws. The underwater tank was not a failure of engineering. It was a failure of leadership. In the end, the underwater tank story is about ambition outpacing reality. It was a weapon that promised to rewrite the rules of war, but it was too complex, too expensive, and too late. It was advanced for its time, so advanced that it could not survive the harsh realities of World War II. For Karl Heinrich and his team, it was a labor of love and frustration. They built something remarkable, but they built it for a losing cause. Today, as we look at modern amphibious vehicles, fast, reliable, and designed for real-world combat, we can see the underwater tank's DNA. It was a pioneer, even if it never got a fight. August 12, 1943, the day of the first open water test, remains a poignant memory for those who worked on the Cetaphil. The tank gliding through the Baltic, the crew's relief when it surfaced, the hope that it would change the war, all of it now a footnote in history. But the underwater tank's legacy lives on in every amphibious vehicle that crosses a river or lands on a beach. It is a reminder that even failed innovations can pave the way for progress. Germany's World War II underwater tank was too advanced for its time, but in the end it was not a waste. It was a step forward, one that the world would eventually follow.